Let k be a positive integer and define a sequence of positive integers a1, a2, and so on by a1 equals 1 and an plus 1 is equal to an plus k to the power of an for all positive integers n. So that there exists infinitely many primes p such that for any integer r, there exists an index m such that a sub m is equivalent to r modulo p. So let's first understand what our problem statement is saying. For any integer r, we want to find a term in our sequence that is equivalent to it modulo p. So might as well just consider r to be 0, 1, all the way to p minus 1. Because if it were anything different, we could just reduce r modulo p. So therefore, we want to show that the sequence covers all possible residues modulo p for infinitely many primes p. Now let's look at some small cases. For example, the k equals 2 case seems pretty difficult in its own right. The k equals 1 case makes the sequence just a sub n is equal to n, which makes it trivial. So let's try out the k equals 2 case. Then an plus 1 is equal to an plus 2 to the power of an. So we should compute a few terms first. So we first have 1, then 1 plus 2 to the power of 1, and then 1 plus 2 to the power of 1 plus 2 to the power of that. And then we have this next term, and then 2 to the power of So this is the fourth term in our sequence. So as we see, it gets messy real quick. And we want to figure out some way to deal with this mess. So consider taking this modulo p for a prime p. Then we have 2 to the power of 1, and then and then 2 to the power of 1 plus 2, and so on and so forth. So all the activity seems to be happening inside the exponent, because that's where our other term is. And when we take it modulo p, by Fermat's little theorem, it loops once every p minus 1 iterations. Thus, we would really like for this top number here, the number in the exponent, to be divisible by p minus 1 at some point, because then this entire term here just evens out and we have an arithmetic sequence. And if you look back at the problem, if we have an arithmetic sequence, then we will cover every single residue because 2 to the an is relatively prime to the prime. All right, so now we can see when this evens out modulo p minus 1. And we have these humongous powers of 2 here, so might as well make p minus 1 equal to some power of 2. So we would require p equals 2 to the power of k plus 1. And the only primes of this form we know are the Fermat primes. So 2 to the k plus 1. So if infinitely many Fermat primes existed, we'd be done. But there's a catch. We do not know if there exist infinitely many Fermat primes. In fact, after 6, 5, 5, 3, 7, we do not know of any more Fermat primes. So how do we deal with this issue? Well, if we only care about primes, then we could get this to even out, but we can try out the evening out idea with a general number of this form. So consider just 2 to the k plus 1. And this does not need to be prime. And consider what happens when you look at this modulo this number. Then eventually this number will even out modulo 2 to the power of k, because it grows arbitrarily large. So that means that if like a is equivalent to b modulo 2 to the power of k, then 2 to the 2 to the, or like 2 to the a is equivalent to 2 to the b modulo 2 to the k plus 1. And we want this to be true, but it's not, because whenever we go up to the k, then it ends up being equivalent to minus 1. So we have to, in order to counter that, we need to make this an extra plus 1. And that does not affect our argument at all. So now that we know that it evens out whenever we have 2 to the k plus 1, we just need to show that there exists infinitely many primes p dividing this number. But then there's this theorem inside number theory called Kobayashi's theorem. So basically what it says is that if you have an infinite set S, so we have S is an infinite set of positive integers, and finally many primes p divide any element of S. For example, S could be the powers of 2, but S cannot be like the set of all prime numbers, because that has infinitely many prime divisors. Then S plus any non-zero constant, so like S plus 1, for instance, which would yield this set, so 2, 3, then 7, so on and so forth. This has infinitely many prime divisors in it. So infinitely many primes are a divisor of some element of the sequence. So let's see how to apply this to the problem. So we want p dividing 2 to the power of k plus 1. So we would like our sequence to be 2 to the 0, then 2 to the 1, then so on and so forth. And this clearly has finitely many prime divisors because, well, the only prime divisor can be 2. So therefore, when you add 1, Kobayashi's theorem tells us that infinitely many primes p exist which divide this number here. And when we use this prime p in our problem statement, we get that our problem condition is satisfied. So therefore, we've solved the case for k equals 2. Now let us solve the case for the general k. We can try employing a similar idea, where we take a prime p dividing k to some number m, maybe plus 1, because we used plus 1 last time, so let's see if plus 1 works this time. Then these terms grow humongously large, so that means that this term evens out modulo k to the power of m. So therefore, the sequence is eventually constant modulo k to the power of m, which would mean that 2 to the power of an, we would want it to be constant mod k to the m plus 1. But the problem here is that this should be a k, sorry. But the problem here is that k to the m is equivalent to negative 1, not positive 1 as we'd like it to. So if we want it to be positive 1, modulo some number, then we want it to be minus 1 here. So let's take p dividing k to the power of m minus 1. Then this is indeed true. So k to the m minus 1. And therefore, we end up, eventually, we're going to only add a constant term to the sequence at some point. And this constant term, we know it's not equivalent to 0 modulo k to the m minus 1, because we're looking at a power of k here, and that can never be 0. So with this arithmetic sequence, we cover all possible residues modulo p. So now we just need to show that infinitely many primes p divide numbers of this form. But this is true by Kobayashi's theorem from earlier. Recall how we did this for 2 to the power of m plus 1. We can do something similar for k to the power of m minus 1. Therefore, when we take such a prime p, we end up getting that the problem condition is satisfied. And therefore, we are done. Thank you so much for watching this video. Please subscribe if you'd like to see more videos.